Hello everyone. Today I'm going to talk about holographic entropy inequalities. My name is Joydeep Naskar, and this work is done with Ning Bao and Keiichiro Furuwa. The ADS safety correspondence, as you know, is a duality between quantum gravity theory in an ADS space to a CFT living on its boundary. The entanglement in the boundary is related to the geometry in the bulk. Most notably, the Ru-Takanagi formula relates the entanglement entropy of a subregion in the boundary to the area of the minimal surface homologous to that boundary region in the bulk, which surface is also known as RT surface. So if someone gives you a geometry, you can draw all the RT surfaces and then you can translate that to a graph model in the following sense. You can partition all your regions cut by different RT surfaces as vertices, and the edge weights of those vertices connected by edges will be given by the area of that RT surface it cuts. Now, if someone gives you a holographic entropy inequality, you don't know a priori if it's true or false. You can verify, but how do you prove that? One way to prove that is to use the contraction map proof method. The contraction map is basically a map between Hamming like hypercubes, which are bit strings between a certain hypercube to another hypercube. It obeys certain boundary conditions and distance conditions. Now, we are going to argue that this contraction map proof method is complete in the sense that if someone gives you a conjectured inequality, if you can find a contraction map, it is a true inequality. If you cannot find one, then it is a false inequality. Here's an example of the contraction map for the famous MMI inequality. We will skip that. So it has been found in our work that the contraction maps have a very natural realization in terms of graphs, a map between a hypercube graph and a partial cube. So this brings us to a triality between holographic entropy inequalities, contraction maps, and partial cubes. So if you want to find all holographic inequalities, you might as well just find all contraction maps, which is equivalent to finding all partial cubes that you can get from hypercubes. So in our work, we fix a hypercube. You can change that hypercube as well, doesn't matter. So let's say you fix an hypercube, which is amounting to fixing the number of terms on the left-hand side of an inequality. And then you find all possible partial cubes generated from that hypercube. Then you can construct the contraction maps from the partial cubes that you get, and then you can use the different homology conditions, different boundary conditions to read out the inequalities. So in this way, you can find all possible holographic entropy inequalities in principle. Thank you very much.